Good morning, madam. Today I would like to present about pressure strength test. Okay, introduction. What is pressure? Pressure strength is one measure of the strength of concrete. It is a measure of an unreinforced concrete beam or slab that resists failure in bending. It is measured by loading 150 mm times 150 concrete beams with span length of at least 3 times the depth. The flexural thrust is an indirect method used to measure the tensile strength of unreinforced concrete. It determines the concrete capacity to withstand bending and deformation force before cracking, which is especially critical for rigid pavement, slab and bridge. Why it is important? Because concrete structures such as pavement, slab and bridge decks are mainly subject to bending. Help in the design and evaluation of concrete pavement and other structure. Then determine the cracking load and load carrying capacity. Ensure safety, durability and serviceability of structure and use as a quality control parameter in concrete. Next is type of flexural test. First, center point loading. A single load is applied at the center of the beam. Simple setup and produces the highest stress at the middle of the specimen. And then third point loading. It is two equal loads are applied at the 1/3 point of the span. Produces a constant bending moment between the loading points and commonly used for concrete pavement design. And the third is 4-point loading. It is two loading points are placed further apart to create a larger constant moment region. Provide a more uniform stress distribution and widely used in research laboratory and for advanced materials testing. Then material use. The main material used to prepare the concrete are cement, fine aggregate or sand, coarse aggregate, water and optional polypropylene fiber or chemical admixture. The concrete is cast into beam mold with dimension of 100 mm times 100 mm times 500 mm. These specimens are then cured before testing to ensure they achieve the required strength. Next is test equipment. Several pieces of equipment are required for flexural strength test. The universal testing machine is used to apply the load until the concrete beam fails, and the loading frame and support roller ensure that the beam is properly positioned according to the testing standard. And a steel ruler or vernier caliper is used to measure the beam dimension accurately before testing. These measurements are necessary for calculating the flexural strength. After that test procedure, the test begins by preparing the concrete mix according to the specified mix design. Next, the concrete is cast into beam mold and compact to remove air warts. After 24 hours, the specimen are removed from the mold and cured in water for 28 days. Before testing, the beam dimension are measured carefully. The beam is then placed on the support rollers in the testing machine and the load is Apply gradually until failure occurs. Finally, the maximum load is recorded and used to calculate the flexural strength, also known as the modulus of rupture. Here we see the properties. This test evaluates several important properties of concrete. The first is flexural strength, which measures bending resistance. It also assesses crack resistance and tensile behavior because concrete is weak in tension. Other properties include ductility, energy absorption, and load carrying capacity. For fiber reinforced concrete, the test also evaluates the post-crack performance, showing how fiber help control crack propagation and improve structural performance. Next is advantage and limitation. The flexural strength test has several advantages. It is a simple and reliable method for evaluating the bending performance of concrete. It accurately represents the behavior of concrete in pavements and slabs under real loading conditions. The test also helps engineers understand cracking behavior and is suitable for evaluating fiber reinforced concrete. Furthermore, it is widely used for quality control and improving concrete mix designs. Then limitation is despite its advantages, the test also has some limitation. It requires larger beam specimen than compressive strength test, making specimen preparation more time consuming. The test also requires specialized equipment which increase the testing costs. In addition, the result can be influenced by specimen dimension, curing conditions, and the loading rate. So careful testing procedures must be followed. Now we see application. Flexural strength testing is widely applied in many engineering projects. It is commonly used for designing and evaluating concrete pavements, airport runways, bridge decks, industrial floors, and parking areas. It is also important for assessing fiber reinforced concrete used in structures that experience bending loads. Engineers use the result of this test to ensure these structures can safely withstand service loads. Now we see the environmental and sustainability. Flexural strength testing also contributes to sustainable construction. Fiber reinforcement improves crack resistance and extends the service life of concrete structures, reducing the need for repairs and maintenance. The use of supplementary cementitious material and recycled aggregates can further reduce environmental impacts. As the result, fewer construction materials are required over time, helping to reduce waste, conserve natural resources, and lower carbon emissions. Conclusion: the flexure strength test is essential for evaluating the ability of concrete to resist bending and cracking under load. It is a key parameter in the design of concrete pavement, slabs, and other structures subject to flexural stress. The tests provide valuable information on the cracking load, load carrying capacity, and overall performance of concrete. The addition of fibers such as polypro- polypropylene can significantly improve the crack resistance and ductility of concrete. Therefore, flexural strength testing plays a vital role in ensuring safe, durable, and sustainable concrete structures. These are my reference. These are the main reference used in preparing this presentation slide. Now that we have a basic understanding of what heavy weight concrete is, let's look at in the more detail. I will explain this definition, density, the material used to produce it, and its main application in engineering. Introduction: heavyweight concrete. Heavyweight concrete is a concrete with a density greater than 2,600 kilograms per cubic meter, while normal concrete has a density of around 2,400 kilograms per cubic meter. It is produced using heavy aggregates such as barite, manganese, amethite, and steel punchings. Because of its high density, it is widely used for radiation shielding in hospitals, nuclear facilities, and also for large counterweight in engineering structures. Why is heavyweight is important? There are three main reasons why heavyweight concrete is important. First, it provides excellent radiation shielding, protecting people from harmful gamma rays, X-ray, and neutron radiation. Second is heavyweight given structures greater stability, making it suitable for counterweights, offshore structures, and areas exposed to strong wind. Third, it has excellent fire resistance and durability, allowing it to perform well in harsh environments and high temperature. Next, we see types of heavyweight concrete. There are four common types of heavyweight concrete. The first is barite concrete, which is commonly used in hospitals and laboratory for X-ray shielding. The second is magnetic concrete, mainly used in nuclear reactors because it provides very high density. The third is hematite concrete, often used in offshore gravity structures. Lastly, steel aggregate concrete use steel punchings or iron shot to achieve very high density, and it's mainly used for counterweight and blast structures. Next is raw material use. Heavyweight concrete consists of several important materials. The first is ordinary Portland cement, which acts as the main binder. Second is water, which is carefully controlled to achieve good workability. Third is fine aggregate or sand, which fills the space between larger particles. Next are aqueous aggregates such as barite, magnetite, hematite, and steel punchings, which provide the higher density. Finally, chemical admixtures, especially superplastic, improve workability while maintaining a low water cement ratio. Next is property of heavyweight concrete. Heavyweight concrete has several important properties. It has high compressive strength, making it suitable for carrying heavy loads. It also has low permeability, which reduces water penetration and improve durability. Another important property is its excellent radiation shielding ability. It also performs well under high temperatures and fire. Finally, its density range of from 2600 to 5000 km per cubic meter, giving it excellent stability. Next is production procedure of the heavyweight concrete. The production of heavyweight concrete involves 5 main steps. First step is the heavy aggregates are select, washed, and graded. Second, all materials are carefully weighed and mixed using a low water cement ratio with superplasizer. Third is strong reinforced formwork is prepared because the concrete is much heavier than normal concrete. Fourth is the concrete is poured in layers and compact using internal vibrator to remove hair warts. Finally, the concrete undergoes extend most curing to prevent cracking and achieve maximum strength. Apart from that advantage, heavyweight concrete offers many advantages. It provides excellent radiation protection, allowing thinner shielding walls. It has high load bearing capacity because of its high compressive strength. It has its low permeability gives it long lasting durability. It also has good thermal resistance, making it suitable for high temperature environments. And its high weight provide excellent structural stability, reducing the risk of overturning. Is environmental and sustainability aspect. Heavyweight concrete also contributes to sustainability. It can use recycled industrial material such as steel punchings and slag. Because of its high density, structures can be built with thinner walls, reducing the amount of concrete required. The heavy aggregate can also be recycled and reused after demolition. In addition, its long service life reduces maintenance and replacement, helping to lower the overall carbon footprint. Then limitation and challenges. Although heavyweight concrete has many advantages, it also has some limitations. First, the materials are more expensive than those used in normal concrete. Second, transportation is more difficult because of its heavy weight. Third, stronger formwork is needed to withstand the higher pressure during casting. It also increases the death load on the foundation, requiring stronger structural support. And heavy aggregates are not available everywhere, so supply can sometimes be limited. Next is references. These are my references used to prepare my slide. Thank you so much.